So the first lecture is Professor Ramakrishnan from CMI Chennai, an extension of the Ramanujan Serre derivative map and some applications.
I thank the organizers for giving me an opportunity for giving a lecture in this conference. So, this is about some extension of some simple derivative map, the theory of modular forms. So, fix the notation now. So, n is set of positive integers, and for Rn natural numbers, let sigma Rn be the divisor function. So, if it's not an integer, then yes, sigma Rn is 0 and sigma R of 0 is 1. These are all the standard notation we have. So, we also write sigma n for sigma 1n. So, for what is the convolution sum we are discussing? This is about the divisor function. If you take two of them and then sum it over integers which is equal to n. So, WAB RS n is sigma R, sigma S, and then we consider only the cases where R and S are odd integers because we are using modular form techniques. Therefore, they are all the coefficients of Eisenstein series. So, RS are odd integers, AB are a natural number, and this is the convolution sum which we will be discussing. They are called the convolution sums of the divisor function. So, when R equal to S equal to 1, this is a usual divisor function sigma, and we simply denote by WAB without writing the R comma S. Further, if one of the AB is 1, then we write only A, and if both are equal to 1, we just write Wn. So, these are all the simplifications. So, evaluation of this type of sums has a long history, so going back to the works of Desge, Glaser and Ramanujan. Various methods were used in the beginning in the literature to obtain explicit evaluation of these convolution sums. To name a few, there is some elementary evaluation using some combinatorial lemma and then use that lemma to get these forms. The other one is to use the theory of modular forms or quasi-modular forms because this sigma is appearing there, this and this equation number 1. What did you say?
In equation number 1, right hand side,
I
don't see how you put L over A and M.
No, because only if it's an integer it will be 1, otherwise it is 0. That's what. It is not an integer, it is 0. So, you take the duplication of the Eisenstein series, that the L by A will be there. I should have stopped there, but it was to.
You're using them.
Yeah, that's. Yeah, that I wrote. No, if n is not an integer, sigma Rn is 0. That.
I don't know what the notation L is not the same as the first one.
Yeah, but here it is. Okay, anyway, the condition is L plus M equal to M. That's all. Okay, so. And there is also another method called the pk parameterization. The pk's are written in terms of theta series. You write your expression in terms of the p and k and then use the parameterization and then they evaluate. This is another method in the literature. A good reference to this kind of results is by a book by K.S. Williams, Number Theory in the Spirit of Liouville in 2011. So, the purpose of my lecture is to look at a basic result in the theory of modular forms and present a simple extension, and as a consequence we get all these kind of sums. So, applying this method one can derive explicit formulas for these and more general types of convolution sums by using explicit basis for the space of modular forms of specific weight and level. So, to begin with, give the basic definition of a modular form of weight k for the full modular group. E2Z be a weight 2 Eisenstein series. Whatever I am writing, mentioning, they are all valid for forms of level also. So, since I am going to use it only for the Eisenstein series, I wrote the full modular group. So, E2 is the weight 2 Eisenstein series, which is a quasi-modular form, and the usual Eisenstein series is given by Ek z is 1 minus 2k by bk, summation sigma k minus 1n e power 2 pi I n z. So, the Eisenstein series are weight k modular forms for the full modular group, and the coefficients involve this the divisor functions. So, if you multiply the two Eisenstein series, the convolution sum of the divisor function will appear. So, the purpose is that if one of them is not modular, the quasi-modular, one of them will be sigma and the other one will be sigma k minus 1. So, that type of sum needs different theory to evaluate. Otherwise, I can use the theory of modular forms to evaluate. So, anyway, I will like to describe this. So, when k equal to 2, we have this Eisenstein series E2, which is not a modular form because it has the following transformation property. So, E2 of Az plus B by Cz plus D is the usual transformation Cz plus d square E2 plus some error term will be there. And because of this property, extra error term is appearing, it is not a modular form, and functions satisfy this type of transformation are called quasi-modular forms. And it is depth 1, so number of error terms will be called the depth. In this case, the simplest case is depth 1 quasi-modular form. I am not going to the details of higher depths. If you take the derivative of this, E2 will have another 2 terms will be there. So whatever the extra terms other than this will be called the depth of the form. So now take the derivative of the modular form, the transformation here. We take this derivative of this one. We have f dash of the transformation is given by Cz plus d power k plus 2 f dash, and then this one extra error term comes. Therefore, derivative of the modular form is not modular. It is a quasi-modular form of depth 1. Now, since the derivative on E2 have the same type of the transformation with the extra term, so this is one extra error term here, one error term, I can cancel this. So, a linear combination of this E2 and f, and this becomes a modular form. So, take the derivative of f, 1 by 2 pi I minus k by 12 E2f. This combination cancels the error term, and it behaves like a modular form of weight k plus 12 for the full modular group. So, the result holds for any weight, any level also. And if f is a cusp form, the resulting form is a cusp form. So, we denote this map by theta k, which is the df. D is cancelled, including the 2 pi factor, I put in df is that minus k by 12 E2f is that. So, this is the literature called the Ramanujan Serre derivative map. The reason is that the Ramanujan one first considered this type of one for the Ramanujan delta function. Later on, Serre generalized for any weight k. Therefore, this is called the Ramanujan Serre derivative map. They will just give some. The first example of a cusp form is weight 12 is given by delta Z, which is the linear combination of E4 cube and E6 square with 1 by 28 is a factor out. So, tau n's are integers, and this is called the Ramanujan tau function, which was extensively studied in the paper of Ramanujan 1916 paper. So, by taking the logarithmic derivative of delta, so he observed that the ratio of delta dash by delta is the 2 pi times E2 of Z. So, using this relation, he gives a recursive formula for tau n, that is, then he lists the first few values of tau, and then he made the famous conjecture for the estimation of tau n. The whole 1916 paper is around the estimation of the tau n, and he gives many examples justifying his kind of conjecture. Note that by applying the theta 12 operator on delta, we have delta d delta Z minus E2 delta is a cusp form of weight 14, but there is no non-zero cusp form of weight 14, and therefore it should be 0. Therefore, d delta Z is E2 of Z delta, which is exactly the observation in the previous slide. It is exactly this one. Okay, the above operator was considered by Serre for any weight k modular form, and this is the reason for the name of the operator. In the same 1916 paper, Ramanujan extensively studied the convolution forms W11 RS, where there is no duplication. So, there is no, the DAB is 1 in this case. So, there is no duplication here, just take only the Eisenstein series and multiply, and then get the convolution sum. That is what he did in his paper. So, when AB equal to 1 and RS, one of them will be 2, and then you can take both R and S are positive integers. And then what he does more generally, he gives the convolution sum in terms of a main term and error term. Main term comes from the part of Eisenstein series, and the error term comes from the part of the cusp forms, and gives an explicit estimate for the cusp form. The whole idea for him to evaluate this one is to show that the cusp form has some kind of growth estimate, and he compares with his conjecture and then what it should be. That is the line of argument, and there are 3 separate cases he considers in that paper. Also, the next slide will give some exact formulas obtained in the Ramanujan's paper. So, this is the one which taken. The notation is slightly different because he added 2 extra terms, that not the same sum which we consider. Some 2 extra terms are added in the sum. So, some one means the 0th term is also added. So, we put the 1 to m minus 1 in that. Here is 0 and m is also included, so that we get these formulas. Okay, so explicit evaluations. So, when RS are odd integers greater than or equal to 3, then the sum can be calculated using the theory of modular forms. Since the sum is part of the Fourier expansion of the modular form E R plus 1 S Z and E S plus 1 Z, both are modular forms. and therefore it is a model weight is a weight R plus S plus 2 modular form. Therefore, you can express this in terms of a basis, and then whatever comes out the coefficient is the convolution sum. So that is easy when both R and S are greater than or equal to 3. Only the difficulty comes when one of them is equal to 1. So we need to consider the case when one of them is 1. In this case, one can use either the theory of quasi-modular forms or other techniques, as I mentioned in the previously, that to get this form. So we give below the list of cases where these sums have been studied in the literature, and I am not going to the details of what. And so AB is given by this set of values, and these are exactly values of AB, and in that case what will be the level of the form. And the authors, not a complete list, okay, Besque, Glaser, Ramanujan, this case considered 1 was considered earlier. Cooper, Lemire, Cho, Williams, Huard, He, Eigen, Alaka, Pesijoglu, and including my work. Okay, it is not a complete list. So you can see the references in the literature, you can see many papers in that. So in this talk, first we consider the Ramanujan Serre derivative map and extend this in a simple way so that we can evaluate the convolution sums WAB, 1 K minus 1. One of them is 1. One of them is 1, other one is any odd integer using the theory of modular forms. So another thing is that Ramanujan also proved that the derivative of E2 and E2 square, this combination is a modular form of weight 4, which implies that the derivative of E2 and E2 square gives E4. And this also gives a convolution sum of sigma WAB in this case. So we also give a simple extension of this result, from which we evaluate the convolution of WAB for any AB in terms of a basis for the space of modular forms of weight 4 and level AB. The advantage of our method is that it avoids the use of structure theorem for quasi-modular forms in evaluation of the convolution sums. So the known convolution sums in this case are, again I have given some references, Ramanujan, Lahiri, Cheng, Williams, Royer for this case, Huard, Cheng, Williams, Belfi, Royer, Yao, Cheng, Williams, Koklus, again 1, the weight K is equal to 6, Ramanujan, wherever this one Ramanujan will appear, all the cases he considered. So this is a joint work with Vrindavan Sahu and Anup Kumar Singh. This whatever I am writing, this one is appeared in Ramanujan in 2023. So consider this the derivative differential operator theta K AB, which is B times df of Bz minus K by 12 A times E2 of Az into f of Bz. So one can show that this takes modular form of weight K into K plus 2 and level n dash, where n dash is the LCM of n times B and A. So to simplify the notation, we will be writing this B into df, B as a script df, and this gives a Fourier expansion of this one. So when B equal to 1, both the script D and the normal D both are same. So in view of the above remark, we modify the definition of the theta operator as the script D of Bz minus K by 12 A E2 is. So if I take F as isosceles series Ek, our convolution sum WAB 1 comma K minus 1 will come out. Okay, only thing is that we have to find a basis for the space of weight K plus 2 modular forms of level AB, and then once you write this, express this in terms of a basis, and then compare the coefficient, and finally we can derive it. Our next result is about extending the Ramanujan's observation that the 12 times dE2 Z minus E2 square is a modular form. So what will be the, if you duplicate this Z by some AZ and then this Z by BZ, this is the combination 6A by B derivative of E2 of AZ, 6B by A D of E2 BZ minus E2A Z E2 BZ is a modular form in level 4 and weight 4 and level AB. So in terms of the D operator, this is a modular form of weight 4 level AB. Therefore, again finding a basis for M4 of AB equivalent to finding the convolution sum in WAB with R equal to S equal to 1. So before we state our theorem and examples, we shall make some remarks. In 2019, Eigen also evaluated the convolution sum W1Pn, WP1P2 and W1P1P2, where P, P1, P2 are prime numbers. The method in this work is different from our method, though both of these works make use of the fact that the resulting function is a modular form. Eigen used the fact that E2Z minus T, E2Tz is a modular form of weight 2 and level T. And it is also noted that in his work, Eigen obtained the required convolution sums by using the already known W1n. So he has to use either use W1n to get the final result, but in our case, I think we don't need to use this previously known W1n. That is the only difference. So as further generalizations, we use the operator theta on the modular form of weight k plus 2 with f equal to ek, and on theta 4 a1 on modular form weight 4 given by the second one to get explicit expression for a different type of convolutional sums where the derivative of this function will appear here. Here also the derivative of this one will appear. And this is one of them is 1 and both are 1. Rs equal to 1 k minus 1 and 1 1 1. So as a consequence of this modularity conditions, we have the following corollary. So k greater than or equal to 4 be an even integer and f z is ekz. If a and b are relatively prime, and then there exists a constant alpha I, and this is the dimension lambda k plus 2 ab is the dimension of the space of modular forms of weight k plus 2 level ab. Then you express the WAB 1 k minus 1, this is a required convolution sum in terms of a linear combination of the basis elements up to this extra divisor functions. So Bk is the Bernoulli number appearing in the kth Bernoulli number appearing in the definition of Ek. So this is what we evaluate. So proof is simple because you just, as I mentioned though, you express this as a linear combination and compare the Fourier coefficient, we get it. Similarly, by using the modular property of the 4, which is the weight 4 modular form, one can get the WABN in terms of a basis of weight 4 level AB form, and then this extra terms coming from the evaluation of the comparing the coefficients. Going fast. So examples using our theorem. So when you take the AB equal to 3, 5 or 215, and this is the example from using our method, I get it. Then W215 is this, where the tau k n j is nothing but the nth coefficient of a new form of level n, weight k, and there is more than one new form, the subscript j will be there, 1, 2, 3. Otherwise, if there is only unique one, and then there is only, here there is only one new form of level 5 weight 4, therefore tau 4 pi. There are two cases here, the level 15 weight 4, there are two new forms, therefore 1, 2 is mentioned. So next second one is the WAB 1 k minus 1, formulas in this case when k equal to 4, and then when k equal to 10, AB equal to 1, 3. Some examples I gave. So in a recent work, Koklus again appeared in Ramanujan journal, obtained the convolutional sums WAB where AB equal to 68, and there are 5 convolutional sums in this case. So he obtained a basis for the space of modular forms of weight 4 on gamma 0 48, and as an application he will derive a formula for the number of representations of a natural number by this type of quadratic form. So 8 squares if there, with the first 4 squares add up and the second 4th set of squares put the coefficient 17. So it is a, one can show that this lies in a modular form of weight 4 and level 48, and therefore he find a basis, and using the convolution technique he has given. He used the same fact which was used in Eigen's work, the fact that E2Z minus A E2 of AZ is a modular form of weight 2 on gamma 0A. The above result of Koklus is a consequence of our main result, which gives a general formula for the convolution sum WAB. So that's what we want to mention. So by repeated application of the derivative map, extended version of our one, we further obtained the following convolution sum sigma L sigma k minus 1 m, L sigma m. The reason is that there are several results appearing in the literature, but evaluation of this one using different methods. We wanted to unify the finding these terms in a uniform way and using modular forms. So examples again. So another one is that the triple convolution sums. This paper also joint work with Brindavan and Anup. This appeared in IJNT. So we have used the results described in the previous previous part, and extended our method to evaluate triple convolution sums. So where in the previous case we have only the 2 divisor functions, now we have the 3. In principle, one can get any number of divisor functions, and method may be worked out in general. We have not worked out the details, but the method works in general. So to get this triple convolution, we also need the following 2 types of convolution sums. One is L sigma RL sigma S, and then one is the sigma M sigma R sigma S. I put a tilde here to so that this is duplicated. B tilde means this function is duplicated, the derivative. This is nothing but if you take the derivative of E S plus 1, this M into sigma Fm will come, okay, when you do the Fourier expansion, and then multiply with ER plus 1, we get this convolution sum. Therefore, the second part is taking the derivative, this first part is taking derivative. So, simplify the notation, I write like this. And these two sums have a following relation involving the WAB sum. So, when you take the A tilde and then B tilde, putting A and B together give you the WAB RSM. So, this is a nice relation between them. So, we proved the following result concerning triple convolution sums. So, when you take the RS equal to RS and T equal to 1, the WD1, D2, D3 is given by, this is a, again linear combination of basis elements of weight 6 and level D, where D is the LCM of D1, D2, D3. So, we obtained similar results when R is equal to S equal to 1 and then T is greater than or equal to 3 and R equal to 1 and S and T greater than or equal to 3. There are two other cases. When all of them are greater than or equal to 3, directly one can use modular form technique. Otherwise, we have to use some this kind of method. The above triple convolution sum is obtained as follows. If first you consider the E2 derivative combination, which is a weight 4 modular form of level 1, where N1 is the LCM of D2, D3, and then apply the theta operator on this to get the triple convolution sum. So, now apply the theta 4 D1 1 to this particular F, we get this triple. Actually, E2 D1, E2 D2, E2 D3 will give you the triple convolution sum. Therefore, you multiply this expression by 3 by D1 and then compare the coefficients and then we get the square result. Okay. As an application, one can find explicit formulas for the number of representations of an integer by certain quadratic forms. So, for example, I give two examples. One is sum of squares and one is this sum of x1 square plus x2, x1 x2 plus x2 square, a combination of this type of quadratic forms and then the 2k variables. So, one example I will just quote here. One is that Q8, you take the x1 square, x1 x2, x2 square and x7 square, x7 x8, this type of quadratic form in 8 variables. And then you take the combination of Q8 and then Q8 twice and the third 8 variables you put the coefficient 2 and then you keep the first one and then first, second and third you put the coefficient 2. So, both are 24 variable quadratic forms and if you compute and RQ24IN denote the number of representation of a natural number n by this quadratic form. So, here are Q1, this is called the Q1, this is Q2. For RQ1n, this is first one, the second, the last one is duplicated by 2. Okay, therefore, we have S8n is for the 8 variable, for the Q8, we know the formula which is given by 24 sigma 3n plus 216 sigma 3n. Since we have 3 parts are there, this triple convolution sum play a role here. So, now substitute the S8n formula and then we get all type of double convolution and triple convolution appear here. Substituting these values of the convolution sums, I get a formula for RQN, a similar procedure for the 24Q2, Q24-2. Just and one more thing which I want to mention, that this is just application I wrote, but without this application directly I can use modular form technique to get a formula for this. Anyway, when you do this one can prove that this particular one is weight k modular form of level 3, because when you take x1 square plus x1 x2 x2 square, it is a level 1 gamma 0 3 with character will appear. So, then I am taking 2k of them, no? So, therefore, it will be weight k parts of the weight 1 form. Therefore, this will give you a weight k modular form of level 3 and this will give you a level 6 form and this also will give a level 4 form. Therefore, directly one can use kf modular forms and get the formula, but if you want to use the convolution sums, and this one gives you that also. And probably whatever the method we use, the resulting formula will be the same. So, now I finish this. Happy birthday to Kalyan and Sriji. Thank you.